Okay, so hello, good afternoon. So I will start now.
Good afternoon, ma'am.
Yeah. So I will introduce myself a little bit. So I am Anjali Degi. I am currently pursuing PhD in IIT Kanpur as a theoretical and computational chemist. So yes, for today's session, I will start from 2014 problem. So I will share my screen now.
Hello everyone. In this video, I will be solving GATE 2014 Chemistry question number 12. This question states that in atomic absorption spectroscopy, the atomization
I think the quality is not that good, so let me refresh it. Okay, so yeah, it's under process.
normal.
Question number 22. Hello everyone. In this video, I will be solving GATE 2012 Chemistry question number 22. This question states that the complex with inverse spinel structure is. We are given with four different options. So before moving into the correct option, let's move into discuss some basic.
Spinal structure is a series of compound having combination of two oxide so it is a mixed oxide of divalent and trivalent metal ion. Okay. By saying divalent, that is A plus 2, it will form oxide AO, and a trivalent metal ion like B plus 3 will form oxide B2O O3. So my spinel will be AB2O4. Okay. Now there exists two type of spinel. One normal spinel and other one is the inverse spinel. So for normal spinel, the spinel structure is such that the oxide ions are arranged in CCP is such that oxide ion are arranged in cubic close packing CCP and divalent ion is present in 1/8 of tetrahedral void and the trivalent ion is present in half of octahedral void. Okay, so this is the normal spinel. We can write it as this A, which is a divalent. It is present in tetrahedral void. B, which is the trivalent metal ion, present in octahedral void with O force. Similarly, in inverse spinal, so in inverse spinal, what will be my trivalent ion gets distributed equally among octahedral and tetrahedral void, okay, and my divalent metal ion, that is A, is occupy the octahedral void, okay. So here my trivalent ion is equally distributed between tetrahedral and octahedral void. Okay. So to distinguish between these two, to identify the spinal, we take the help of crystal field splitting energy, that is CFSE. So we calculate the CFSE of both the metal ion, that is divalent and trivalent, and then compare these two such that if my B plus 3 CFSE in octahedral field, if it is greater than the CFSE of A plus 2, it will be a normal spinal. So similarly, if the CFSE of my trivalent metal ion is less than the CFSE crystal field splitting energy of my divalent metal ion, then it will be a inverse spinel. Okay. Let's just note some tricks. Number one, that the CFSE of a non-transition metal is 0. And number two, if both A plus 2 and B plus 3 metal ion are non-transition metals, then they belong to normal spinel. Okay. Now, talking about the crystal field splitting energy, CFSE, in octahedral field. Here, because it is a oxide, mixed oxide, so we have a weak field complex. It will be a high spin complex. So our metal will experience, it will be a high spin complex or a weak field complex due to the weak field ligand. And since my O4 occupied the CCP structure, that is why it is a octahedral field. So the splitting energy for the octahedral field for D, it will be something, it will be like so the splitting energy for D orbital in octahedral field is this is DG, this is T2G, this is D orbital, this is my energy. So this is D XY, DYZ, D ZX, and this is D x square minus y square and D z square. Okay, and the energy is this is 0.4 minus 0.4 del naught, and this is plus 0.6 del naught. Okay.
So the complex given is the cobalt 3O4. So here you can see that to get the structure as normal and inverse, we have to compare the CFSE. So the CFSE of cobalt plus 2 ion is we can calculate by writing the electronic configuration and then considering the weak field and octahedral, that is the high spin distribution in the T2G and EG levels, energy levels, and then the CFSE of cobalt plus 2 will be minus 0.8 as we calculate. So the CFSE of cobalt 3 plus ion is, if we consider the same condition, will be by the electronic configuration of 3d6 equal to minus 0.4. Okay, but here the point to be noted is that even in the presence of the weak field ligand, that is O4 here, the cobalt 3 plus ion is a low spin D6 ion. Okay, so here even in the presence of the weak field. So it should be giving us the high spin configuration, but cobalt 3 plus doesn't give us the low spin d6 ion. That is due to the high charge on the cobalt 3 plus. This is one exception. So by considering this, we calculate the CFSE as 6 into minus 0.4 equal to minus 2.4. This is all the unit is in delta naught. Okay. Yeah. So the higher CFSE is for the 3 plus ion. So therefore this will be, therefore it is a normal spinel. Yeah, correct. Because cobalt 3 plus have a higher CFSE than cobalt 2, hence the cobalt 3 plus will occupy octahedral void, sides or voids. Okay. Now for Fe3O4, similarly for Fe3O4 we will write down the electronic configuration and then calculate the CFSE. As here for the Fe2 I have calculated as minus 0.4 delta naught, and Fe3 since it is 3d5, so it will be equal to 0. Here you can see that the CFSE for Fe2 is greater than Fe3, and hence Fe2 occupy the octahedral site here. Hence this will be the inverse spinel structure, okay, or complex. Now coming to the another structure that we were given as the Mn3O4, correct? Then we have to calculate Mn2 and Mn3 CFSEs. So Mn2 CFSE, you can write the electronic configuration as argon 3d5 equal to 0 and Mn3 as argon 3d4. So this will be minus 0.6 delta naught, and this you can easily compare that the CFSE of Mn3 is greater than Mn plus 2, and hence Mn plus 3 will occupy the octahedral voids or sides, giving us the normal spinel. For MgAlO4, for this structure, you remember the tip, that is the MgAl are both non-transition element, and hence the CFSE for both of them is equal to 0. Now the size of Mg2 plus is much greater than MgAl. Aluminium 3 plus, and hence Mg2 plus will occupy the tetrahedral site. Al3 plus will occupy the octahedral site, and hence it is a normal spinel. Okay. Now for this given question, we arrive at a correct option as B, which is the inverse spinel structure here. I will refer you to go through the reference lecture 48, perovskite and spinels, by Professor Madhav Ranganathan, Department of Chemistry, IIT Kanpur. Okay, so this is the link below. Thank you. So if you have any doubt, you can type or ask, or else I will move forward. Okay, so I'm moving forward. So my voice is clear, right? Okay, so this is a problem from GATE 2013 chemistry question number 37. So this state that the moment of inertia of a homonuclear diatomic molecule, so we are given with the moment of inertia, that is I, that is 7.5 into 10 to the power minus 45 kg meter square here. We have to calculate we are asked to calculate the rotational partition function at 500 Kelvin. Okay. Now, for the calculation, just brushing up the basics, that is the rotational energy level of a diatomic molecule is given as E rotational equal to B, capital J, J plus 1, where J is my rotational state or quantum number, okay, which is equal to 0, starting from 0, 1, 2, 3, etc. Here my B is the rotational constant. The unit is generally used is the centimeter inverse. It is equal to h, which is Planck's constant, upon 8 pi square capital I, which is my moment of inertia I, and C. Okay. Yeah. I think C should not be there, so I will check that out. So the equation 1 for energy will become Ej is equal to J plus 1 h square upon 8 pi I. The rotational partition function is given as Q rotational is equal to kBT. This is the Boltzmann constant. K, T is the temperature in Kelvin, upon B, which is the rotational constant we declared earlier. So for this, we have to note that for a homonuclear diatomic molecule, rotating the molecule by 180 degree, it brings the molecule into a configuration which is we call as indistinguishable from the original configuration. So this lead to the overcounting of the accessible state, correct? So we, for the correction factor, we divide our Q rotation by sigma. This is known as the symmetry number. And for a homonuclear diatomic molecule, you will find out that this is equal to 2. So that we will divide our Q rotation by 2 here. So this symmetry element sigma that we introduce, it is the number of different ways a molecule can be rotated into a configuration indistinguishable from the original one. So basically, if you have gone through group theory basic or starting from the symmetry elements and etc., so you must have calculated n there, so which was equal to 360 degree upon the number of rotation you need to do to get the indistinguishable, or theta, that will give you the indistinguishable configuration. So that was, for example, the homonuclear diatomic molecule, that will be equal to 180 degree. So 360 by 180 will give you 2. So that is what is our symmetry number here, sigma. Okay. So the general expression of rotational partition function for diatomic and linear polyatomic molecule will be Q rotation is equal to KT upon this is my rotational constant B divided by sigma, that is my correction factor I did, that is symmetry number. So here some note you can take, that sigma is equal to 1 for heteronuclear diatomic molecule. Okay. So for heteronuclear diatomic molecule, the rotation you will give to get the indistinguishable will be 360 degree. Correct. So that will give me sigma equal to 1. And for homonuclear, you will give only 180 degree rotation and you will get the indistinguishable structure. That is why you have sigma equal to 2 for homonuclear diatomic molecule. Similarly, for symmetrical linear polyatomic molecule, example, what I mean by this is that for linear like this, so it is symmetrical, it is linear, but it is polyatomic. Okay. Or CO2, you can take the example. So for this also you will have sigma equal to 2, and sigma for unsymmetrical linear polyatomic molecule, for example N2O, you have sigma equal to 1. So this is some basic. Now moving to our problem, as we are given. So we were given the moment of inertia which was 7.5 into 10 to the power minus 45, And the rotational constant, you can write it as h square upon, that is Planck's constant square upon 8 pi square upon I. So we are given with the homonuclear diatomic. So for homonuclear diatomic, you have the correction factor or symmetry number as sigma equal to 2. This we will use in a Q rotation expression. So our Q rotation expression becomes, it was KT, it was KBT upon this B. So you can just simplify or expand the Q rotation expression, and then by putting the value of each, like moment of inertia is given in the problem. Kb, as you know, it is a constant, Boltzmann constant, 1.38 into 10 to the power minus 23. T is given as 500 Kelvin itself. Sigma is 2, and my h is my Planck's constant taken and doing the square of it, and you will calculate that my Q rotation is equal to 4690. So I can just write it as Q rotation is equal to 4690.10, correct? Yeah. So again, for this, here you can write the moment of inertia of the homonuclear diatomic molecule. You calculated 4690 as your Q rotational, that is the partition function. So this is the value you calculated. So for reference, I will recommend you to go through the lecture by Professor Sandeep Paul, lecture Rotational Partition Function, Department of Chemistry, IIT Guwahati. This is the link below. Yeah, so thank you. So any doubt from this?
No, ma'am.
Okay. So I will move to another problem that we will solve.
Hello everyone. In this video, I will be solving GATE 2014 Chemistry, question number 12. This question states that in atomic absorption spectroscopy, the atomization process utilizes. So in atomic absorption spectroscopy, let's discuss the basic of it. So here, the atomic absorption spectroscopy, AAS, is a spectroanalytical procedure for the quantitative determination of chemical elements using the absorption of optical radiation. Okay, that is light by free atoms in the gaseous state. So the atomization process is very important here, because we take our sample and then we atomize it, that is we free its atom in a atomic states or gaseous state, such that it can then absorb it can do the absorption of optical radiation. That's why it is known as the atomic absorption spectroscopy, because we want we are doing this because we want to determine the chemical elements, that is the atoms. We need to find out the chemical elements which makes our sample or a molecule. Okay, and then to determine that chemical elements, we first need to free our atoms, and hence that is what the atomization process is in the gaseous state. The atomic absorption spectroscopy is based on the absorption of light by free metallic ions. Correct? Now, so in analytical chemistry, this technique is used for determining the concentration of a particular element Okay, it can also determine, not only it can identify the element, also it can determine the concentration of particular element, the analyte in a sample to be analyzed. Okay. And in order to analyze a sample for its atomic constituents, it has to be atomized, as I discussed in the first definition. The atomizers here are most commonly used nowadays are flames and electrothermal, that is the graphite tube atomizers. So for the atomization process, we use atomizers, and those are actually of basically two types, that is the flame atomizers, okay, and the electrothermal atomizers. So the most commonly used one are the flame atomizers. So in this flame atomizer, the principle is the air acetylene flame with a temperature above 2300 degrees Celsius and nitrous oxide system. So with a temperature of 2700 to 2700 degrees Celsius, the flame in addition this offer the reducing environment, okay, and so being ideally suited for the analytes with high affinity of oxygen, and such that these atomizers uses flame to atomize our sample, and hence we can achieve the free atoms in the gaseous state, and then we can do the atomic absorption spectroscopy of that. Okay. Yes. So here it is a block diagram for the atomic absorption spectroscopy. Okay. So here you can see that the sample is put on atomizer here, and then the radiation source we take. So atomizer make my sample, the free atoms will be here. Okay, like I can draw it as a cloud. So these are my free atoms of my sample. So after passing through the atomization process, and after that the radiation source uh, will be the will so this radiation source is actually held responsible to for my atoms to observe or interact with the radiation, and thus it absorbs some radiation, and hence finally we know that what kind of wavelength or what wavelength of light my atoms or whatever constituent particles have observed radiation of, and we determine after that only the elemental, we identify the element and also the concentration using the BL. So here here, and this radiation of light my atoms or whatever constituent particles have observed radiation off, and we determine after that only the elemental, we identify the element and also the concentration using the BL. So here we also apply the principal technique is that we use the atomic absorption spectroscopy of any sample in order to access the concentration of the specific analytes within it. Okay, so it requires some standard non-analyte content to establish the relation between the measured absorbance and the analyte concentration, and we also relies therefore on the Beer-Lambert law here. Okay, so these two circles are focusing lens, okay, and nothing else. So this is a little bit of understanding of what is happening in the instrumentation of my atomic absorption spectrometer. So now that we know that in atomic absorption spectroscopy, what was asked us that the atomization process that my atomizers utilizes what? Flame, electric field, magnetic field, or electron beam. So I know that we have a flame atomizer which uses heat or flame to atomize my sample. Also, there was another which was electrothermal atomizer. So this atomizer actually uh, uses the graphite coated furnace to vaporize my sample. Okay, so it is again using the heating process of graphite coated furnace, as I have said. So this none of these two atomizers use electric field, magnetic field, or electron beam. Hence, the correct option will be option number A. And I will recommend you to go through the Introduction to Spectroscopy by Dr. Sayan Bakshi. So, capital. Okay, and Physical and Material Chemistry Division, NCL Pune. This is the nptel reference. So, I am attaching the link. Thank you.
So, actually, last week will be last live session will be in the next coming week Sunday. So if you have any particular topic to cover, because some person Aditya, he didn't attend after that, but he requested to teach some tutorial or something. So I don't know if Gunasli have attended, but I took one live session as a whole tutorial for 1 hour. So if you two have a particular topic to cover, so I can take the last session as a tutorial also. You can just tell
Ma'am,
me.
quantum chemistry part, ma'am.
Quantum.
Ma'am, quantum chemistry part. That's angular momentum parts are
Okay, so specifically because
questions.
it's a 1 hour session, so I cannot cover the whole.
Specifically,
So any particular like in
specifically
angular momentum part you are saying. So
angular momentum.
so in that what you
Yes,
do,
ma'am.
you are not able to understand. So what I can teach or cover, if you can give me some specific topic under that, you can search. We have time
Ma'am, that
actually. Yeah. So I will play another video, and in meanwhile, Pranoy, you can give me the specific topic, because even in angular momentum part you are saying. So I will try to cover. So in 1 hour, so you can give me the specific topic, and Gunasli also if you have any topic.
Hello everyone. In this video, I will be solving GATE 2015 Chemistry question number 11. So this question states that which one of the following plots represent an acceptable wave function? So we are given with 4 different wave function A, B, C, D. So before moving into the correct option, let's discuss some basic. So for the acceptable wave function, we have following conditions to be satisfied by the wave function for the particular system or particle. So the function must be a single valued function. And the second point is that the function should, when I'm talking about the function, I'm talking about the wave function psi xt, okay? And the function should be normalized. For normalized, it means that the conjugate psi of psi is psi star multiplied with psi uh, should be equal to 1, from minus infinity to infinity, correct? That is, it must have a finite value, and by finite
Ma'am,
value I mean that
excuse
for
me.
every
Yeah,
single
wait.
value of x, by psi x t should have
Yes.
मैम इको साउंड आ रहा है.
Oh, okay, okay. My mic is on. Yeah.
a single value at particular x, okay? And again, it must be continuous in the given interval. For this, you will see that my wave function should be continuous in the given particular interval for it to be the acceptable wave function. The fourth point is that the first derivative must be continuous on the indicated interval. So that when we are talking about the derivative, so derivative of any function is equal to gives me mathematically the tangent at a particular x. So for any given I will discuss it in the next slide also. So for any given wave function, so at any particular value of x, so there should be only one direction or the tangent. So such that the first derivative must be continuous. Okay. So the last one is a boundary condition must be satisfied by the wave function. For our boundary condition, when you will be discussing or studying the case of, like, for example, a particle in a 1D box, you will see that there are set of boundary condition that my particle follows or my wave function follows is such that that at the boundary my wave function is equal to 0. Okay, so those are some boundary condition. So these are the point for my acceptable wave function. So here, uh, so all the four options that we are given with, if I apply the condition, so at for A, you will see that this is not a continuous wave function. Okay, so this is not continuous. For my wave function should be continuous, there is also the physical meaning, because for this particular region where my wave function has no value, or you can say that it has disconnectivity, so at that point the my particle probability of finding of the finding the probability of finding my particle is 0 there. Okay, and for B option, you can see that this is not a single valued function for a particular value of x. So at any value of x, for example here, you will see that we have a different value of psi xt, which is not the condition that we want for our acceptable wave function. Okay. And for C, you will see that this is a continuous wave function, but here the first derivative is not continuous, because at any peak point or any sharp point, you will see that we have the derivative of this function is not continuous. So here we have different direction of our tangents, and therefore this wave function is also not acceptable. For D, you will see that the wave function follow all the condition, and hence it is the acceptable wave function among the all different options we are given with. Okay, so this is a correct option. And here I am attaching the NPTEL reference for lecture number 4, Postulates Part 1 by Professor K.S. Sebastian, Department of Chemistry, IISc Bangalore. Here is the link below. Thank you.
Yes. So you can give me your feedback. I have taken in every
Yes,
session,
ma'am.
but you were
Yes,
talking
ma'am.
about some
That,
topic.
ma'am, wave functions part of the simple harmonic oscillator. In that part, also angular momentum also covered. Uh,
Okay.
That specific part is the simple harmonic oscillator part.
So
It is
specifically simple harmonic oscillator you want to be covered in detail.
yes, ma'am. That uh, in that that calculations of the average energy and wave functions, etc.
Okay. Calculation of average energy, wave function, etc. Okay. Anything else? I think for 1 hour it will be this much only. But if you have any other topic, I will try. Yeah. So Gunasali, so is it clear to you uh, the problem that we solved today?
Yes, ma'am.
Okay. And do you have any particular topic that you want me to cover?
Ma'am, thermoanalytical chemistry part, TGA, DTA, DCA, that parts. If you have some time, then can you cover this?
Thermoanalytical
That's
chemistry, uh, I don't think
TGA,
I can.
TGA, DTA.
I don't think I can cover that because I myself haven't studied that.
Okay, okay, ma'am. Sorry, ma'am.
Yeah, no, it's fine. But as you, I have told you earlier also, as you are attending other live sessions also, you can ask the other tutors to take such sessions and cover some topic.
Yes, ma'am. Yes, ma'am. Yes, ma'am.
So because it's the end of the, I am having the last session, so that's why I was like that I have to do this. If you have any topic to be covered, actually, before you also some person have asked me to cover some topics, so I wrote it down. I gave one session, but he didn't attended that. So after that I didn't continue with that. So also he asked me for organic material also, so I requested the organic people to cover some topic like that. But the problem is that because the person who is asking us to do the tutorial in the 1 hour session, if he or she is not attending, then so that is the another problem. So it's okay, so I will cover in the next session the simple harmonic oscillator. For thermoanalytical chemistry, I will see that I can. Have you searched for it for any NPTL video you have regarding this
Yes,
topic?
ma'am. Yes, ma'am.
So was it not clear because NPTL video cover in detail?
Ma'am, little but that questions part, question answer part.
Okay,
If you
yeah.
have some questions related that, can you discuss that?
So okay, thermoanalytical chemistry. So in GATE we get the. You have any specific problem in GATE that came in thermoanalytical part?
I Yes, ma'am. Specifically, get.
Okay, so I think I have to check by myself because the questions I picked was from inorganic and physical and thermoanalytical. So you have any problem in hand? You can state it to me so I can get some idea.
Ma'am, if you drop that mail ID, then I can share you.
Yeah, yeah. So sure, I will type my email ID. Yeah, you can send me the problem here, so I will see. So if it is in gate, so I am sure someone has covered the problem, the solved video. So you are doing masters, Pranay?
Yes, ma'am.
From where?
Uh, College of Engineering and Technology, Bhubaneswar.
Okay, okay. So it's a 2 year program or integrated?
integrated programs.
Okay, so it's a 5-year program. Okay.
Yes.
Okay, so for today we are done with the session. So you can leave. And Pranay, you can send me the problem you were talking about for the thermoanalytical part.
Yes, ma'am. Yes, ma'am.
Yeah. So okay, Gunasili.
Yes.
Yeah, thank you.
Thank you, ma'am.